Let's talk about how you can use least squares to perform model regression. As we mentioned in a previous lesson, we can represent a wide range of functions using a linear model of the form y equals x times w, where y is a vector of outputs, x is an input matrix where each row is a set of inputs, and w is a vector of weights for the linear model. Oftentimes, we find ourselves in the situation where we have been given a set of input and output data and want to find the best fit parameters of a particular model. For example, you may fit a line to data and use the slope of the line to determine whether your data is trending upwards or downwards. In this lesson, we will describe a technique called least squares, which will allow us to solve for the weight vector of a linear model expressed in the form above. So what exactly is least squares? It is a method dating back to the beginning of the 19th century that allows us to solve for the weights of an overdetermined system. By overdetermined, we simply mean that we have more data points than we have unknowns. For example, if we're trying to fit a line which has a slope and y-intercept, we need at least 2 data points. If we have only 1 data point, it is underdetermined. The reason we call this method least squares is that we'll find the best weights by minimizing the squared error loss on our data. So the least part of the name refers to the minimization, and the squares refers to the idea that we're focusing on the square error. So imagine that we have a guess for the weights vector that we will denote with w hat. If we multiply this weight vector by our input data, we will get the predicted output of our model, which we will denote as y hat. The error for this weight vector e is simply the difference between our predicted output and the actual output from our data. If we substitute back in our definition of the predicted output, we can say the error is also equal to y minus x times w hat. So this error is going to be an array where each entry is the difference between the predicted and actual output. Keep in mind this difference could be positive or negative. As we mentioned earlier, we are interested in minimizing the error, so we'd really prefer that the error always be expressed as a positive quantity. For example, if the difference between a predicted output and the actual output is minus 2, we would like to denote that the magnitude of the error is 2. This is why we instead use the squared error. If we simply square each of these differences, we can guarantee that the individual errors will always be positive. Rather than squaring each term in the vector individually, we can express this squared relationship in a matrix vector form. What we are interested in finding is the choice of weights, which will give us the smallest value of the total error. We calculate the total error by multiplying the transpose of this vector by itself, which effectively computes the dot product of the vector's entries with itself. The final value is a scalar quantity, which is the sum of the squared error for each of the predicted outputs. Now that we understand the expression that we are trying to minimize, the question is how do we actually find the weight vector w, which minimizes this expression? While there are multiple ways to derive the weight vector corresponding to the least square solution, in this video we will focus on a calculus-based approach. In order to understand how we can solve the matrix vector equation, we will first study the scalar case in order to build our intuition. Specifically, we will focus on a simplified version of the minimization, where we have just a single input, output, and weight. In this problem, given a single input x and output y, we are interested in solving for a weight w that minimizes the error. Now that we have removed the transpose, we can also simplify the expression. Notice, because the expression is squared, no matter what value we have for the input, output, and weight, the error will be non-negative. So before we actually try to solve for the value of w that minimizes the error expression, let's take a look at what this function actually looks like. What we can notice is that because we are looking at the squared error, we have created a parabolic shape for our error function. Because we are interested in investigating the impact of the weight on the error, the dependent variable of our function is the error, and the independent variable is the weight w. You can think that the values of y and x are fixed constants, which are the data that we have collected. So what do we see when we plot our error function against the value of w? Here are a few examples for different sets of inputs and outputs. In each case, we can see the parabolic shape, which indicates that each of these error relationships has a single global minima, or in other words, the error function is convex. So now we know that the given input and output, there will always be a single value of w corresponding to a global minima of the error function. In other words, there's a single value of w which will give us the lowest error. Next, we need to determine how we can find the value of w. If you recall from calculus, we can set the first derivative of a function equal to 0 in order to find that function's minima and maxima. So the first thing that we will do is write out our derivative. As a reminder, we are taking the derivative with respect to the weight w. To calculate the derivative, the first thing that we will do is expand out our terms using the FOIL method. Y times y will give us y squared. The inner and outer terms both give us negative xyw, so we have minus 2xyw, and the last term gives us x squared w squared. The first term doesn't contain any w, so the derivative will be 0. The second term will give us minus 2xy, and using the power rule, the third term will give us 2x squared w. As we said earlier, to find the minima or maxima, we set the derivative equal to 0 and then solve for w. As we saw in our graph, we have a single solution which occurs when w equals x divided by y. We can take another derivative and use the second derivative test to confirm that this value is a minimum of the error function. When we take another derivative, we simply get 2x squared, which will be a positive quantity for any non-zero value of the input x. Thus we have confirmed we have a minimum. Since there's only one point where the first derivative is equal to 0, this is a global minimum. So what did we learn from this exercise? We learned that by taking a derivative of the error expression, we can analytically solve for the value of w that minimizes the error expression. So now that we understand the scalar case of how to solve for the weights, let's return to the matrix vector case. Similar to the scalar case, the first thing that we will do is expand all of the terms. The first term will give us y transpose y. The outer term will give us negative y transpose xw. The inner term will give us negative xw quantity transpose times y. And the last term will give us xw quantity transpose xw. As a reminder from linear algebra, the transpose of the product of two terms can be expressed as the product of the individually transposed terms in reverse order. We can apply this identity to both instances of the quantity xw transpose to simplify the expression a bit. Next, we want to see if there are any other places where we can further simplify. The ones that we'll focus on are the second and third terms. Specifically, let's look at the second term, y transpose xw, and calculate its dimensions. We know that y is an n by 1 vector of outputs, thus y transpose is a 1 by n vector. We know that x is an n by m matrix where each row corresponds to a set of inputs. Finally, we know w is an m by 1 vector of weights that are applied to the inputs. So if we go through the matrix multiplication, 1 by n by m by m by 1, the output of the overall quantity is 1 by 1, or in other words, a scalar. If you think about this some more, it makes sense, as we said that our squared error function is just the sum of all the individual errors. Thus, the terms that add together to give us this error should themselves all be scalars. So since this term is a scalar, one trick we can use is to take its transpose, as the transpose of a scalar is just the same scalar again. If we take the transpose of this term, what we find is actually the same quantity as the third term in our original expression. Thus, our final simplification can just add these two terms together, and we're left with a total of 3 terms. Now we are ready to differentiate. In order to solve for the weight vector that minimizes the expression, we will take the partial derivative with respect to the weight vector. While this expression may look daunting, we can remind ourselves that it is very similar to the scalar expression we looked at previously, just with matrices and vectors instead of scalars. We will use our scalar derivatives to motivate the equivalent matrix vector derivatives. While we don't have time to prove these relationships in this video, I encourage you to show that they hold as an exercise. We will start with the first term. In the scalar case, we said that the term x squared did not depend on w, thus the derivative was 0. In the matrix vector case, the term y transpose y still doesn't depend on vector w, and thus the partial derivative will be the 0 vector. In the scalar case of the second term, we said the w term goes away through the power rule, and thus the derivative was simply minus 2xy. In the matrix vector case, the w transpose term similarly goes away, and we are left with minus 2x transpose y. In the scalar case of the final term, we again use the power rule on the w squared to get 2x squared w. In the matrix vector case, we have a w transpose on the front and a w on the back. When we take the derivative, the w transpose disappears to lower the power, and similar to the scalar case, we get a constant of 2 in front. Now we are ready to solve for the weight vector. Assembling our terms from the previous slide, we are left with two expressions which we set equal to 0 to solve for the minimum. First, we move the negative quantity to the other side of the equation. Next, we divide both sides of the equation by 2. Now we want to get w by itself. We can do this by getting rid of the leading term. Because we are dealing with matrices and vectors, we cannot simply do division. Instead, notice that the leading term is x transpose x, which has dimensions of m by m, and is thus square. This means that we can left multiply both sides of the equation by the inverse of the leading term. As a reminder, if you multiply a matrix by its inverse, the result is the identity matrix, so it is effectively cancelled out. Thus, we have arrived at an expression for how we can calculate the weight vector w from our input and output data. While we won't further discuss this until the next video, I do want to point out that our expression for w requires that the expression x transpose x is invertible. So as a result of all of that calculus and linear algebra, we now have a direct analytical expression which we can use to solve for the weights that minimize the squared error of our model on input and output data. This expression is the least squares solution. The first part of this expression is also sometimes referred to as the Moore-Penrose inverse or the pseudo-inverse. The reason this is also referred to as the pseudo-inverse is based on our original linear model, y equals x times w. If we were able to simply left multiply both sides of this equation by x inverse, we could get the result of w. However, x is often not a square matrix, thus we can't actually take an inverse. Thus, the expression above is called the pseudo-inverse, as it can stand in as the term that pre-multiplies the output vector in order to solve for the weight vector. Now that we've determined the expression for the least squares solution, let's try it out on a few examples. The first example is to find the parameters of a line in slope-intercept form given input and output data. First, we assemble our input matrix. As a reminder from the last lesson, each row will contain one set of inputs. The first input will be the value of x, and the second input will be 1, which corresponds to the weight for the y-intercept. We fill in each row with a set of data to get our full input matrix. Our output vector is simply the concatenation of the output value corresponding to each set of inputs. Next, we plug our output and input into the least squares solution, from which we get a vector with two weights corresponding to the slope and y-intercept, respectively. Finally, we can create some new inputs, x, to plot our least squares solution. In this example, I used a linearly spaced set of values from 0 to 10. Plotting this result on top of our original data, we can see our least squares fit. The second example is to find the parameters of a cubic function to fit given input and output data. Now we can see that we have four weights, a, b, c, and d, that we want to solve. First, we'll assemble our input matrix. Each row will contain one set of inputs. The first input will be x cubed, the second will be x squared, the third will be x, and the fourth will be the 1 corresponding to the function offset. We fill in each row with a set of data to get our full input matrix. Our output vector is again simply the concatenation of our output value corresponding to each set of inputs. Again, we plug our output and input into the least squares solution, from which we get a weight vector with our four model parameters. Finally, we can again create some new inputs to plot our least squares solution. Plotting this result on top of the original data, we can see our least squares fit for the cubic function. Summarizing, in this lesson we showed how we can use least squares to find the best fit model parameters for a linear model given a set of inputs and outputs. Specifically, we showed how we can find these model parameters using a closed-form convex optimization. As hinted earlier, in the next lesson we will look into what we can do if we don't have an overdetermined system, or in other words, the term x transpose x is not invertible. Thank you for listening.